That's too much. Well, the purpose of this work was to try to study the effect of constraint on the JR curves, the resistance curves of standard and non-standard specimens, in order to try to reduce conservatism in ECA, engineering critical assessments. So basically, we have applied a local approach, a phenomenological approach, to try to derive these R curves. So basically, I will try to provide some background and present the specimens that we have tested, virtual tested, which are notch CT specimens and an SCT specimen. And basically write some results and some conclusions on how can we be able to apply these results. So, first of all, what's constraint and how does it affect fracture? Basically, if we have a smooth bar, there is no constraint to lateral strain, to lateral contraction, and there is free flow. When you have a notch tensile bar, for example here, the region up to a certain level of load, the region close to the notch tip may get some plasticity, and this plasticity, the contraction in that part is much larger than in the elastic part. So the stress is in the plane perpendicular to the loading direction, constrained that extension in this direction, and therefore there is an inhibition of plastics flow. So basically, we can see an example of a material here and how the engineering strengths and engineering strengths differ when you machine different notches. So basically, what we want to do is to understand how the energy, which is basically given by the area behind the curves, changes for the different specimens, and which gives us an idea of the fracture toughness. Sorry for this, which gives us an idea of the capacity of the specimen to absorb energy, and the fracture toughness as well. So, constraint give us the level of constraint in a specimen basically gives the amount of energy that the specimen is able to absorb. So we use in testing standards, we use typically SEMB specimens and CT specimens because they provide lower bound values for fracture toughness, because they are highly constrained specimens. But if we test other specimens, and in practice, when we have cracks in our components, shallow cracks in pipes, we know that the constraint level in those components are lower than in these kind of specimens. So we could take advantage of that reduced constraint in our structural integrity assessments, and that's what we want to do here. So this is to provide an example. We work at the ICAM. The ICAM is funded by BP. BP is really interested in trying to understand how defects in pipelines can be assessed in a less conservative way. And we got a huge Excel file with about 17,000 anomalies in a pipe, in a line pipe of about 2 kilometers. And we were decided to understand how these defects were in terms of dimensions and how can we improve the assessments that BP was doing. Because basically what they do now is they recharacterize all their defects into cracks, and they do a basic fracture mechanics approach. So for this simple approach, we analyze the sphericity of these pits in this case, and we understood that most pits, 75% almost, are volumetric. So we could take advantage of that non-sharpness, in a way, that bluntness of the pits and just focus on the critical ones, because these ones, in a way, would be less detrimental in terms of fracture. So we know that constraint changes our capacity of tearing or resistance to crack extension, and this is an example of a schematic of CT specimens, single edge bend down specimens, and a shallow crack specimen. But also we could be able to machine a notch in our CT specimens, and we think that the tearing capacity would also be enhanced. So what if we treat notches as a constraint effect problem? That could provide us some insight into how to assess the problem and how to enhance our structural integrity assessments. So basically, this is what we want to do. We want to reduce our conservatism. If our defects have not gone unstable, so that means that there could be an over-conservative assessment, and basically that our constraint condition in our component is reduced, is lower than that in a highly constrained specimen. So we use a phenomenological approach. We took advantage of some phenomenological observations of ductile tearing, basically saying that ductile tearing is most affected by stress triaxiality, and we have fitted for 4 different materials this damage criterion, which is obtained from notch tensile test, in which the true fracture strain changes with triaxiality by means of a exponential relationship. Basically, we have implemented this within Abacus using 2 different user subroutines, and the critical damage is obtained by means of incremental steps, which depend basically on the incremental plastic strains and the strain to fracture measure in this curve. This local approach is not new. It's very similar to the Rice and Tracy approach, and we have used it to enhance our engineering approach. So, as I said, we have 4 materials, 2 typical pipeline steels, 1 power pressure vessel, reactor pressure vessel steel, and an Inconel material which we have calibrated to obtain these model parameters, data model parameters. So once we have this, which is basically summary in 1 slide, but it's a lot of work because it requires notch tensile test and also finite element calibration of the model. We are able now to analyze our specimens. So as I said, we tested different notch CT specimens and SCT specimens, and we want to evaluate the JR curves. So first of all, we are showing here the level of stress triaxiality, which gives us an idea of the constraint at the tip, or the crack tip of the different specimens, and we see that the SCT, of course, as we were expecting, has a lower constraint, lower triaxiality at the tip of a crack. But also we show here that the notch CT specimens have also a reduced constraint. What we want to do in the future is to use this SCT, the SCT JR curve, to assess blunt defects. So this is part of the FE work, the calibration of the models, and these are the results. We can see here the obtained load versus low line displacement curves for the API 865 material, and although the maximum load seems to be, there's not much difference in the maximum load, the energy given by the by the area below the curve differs significantly for the different notch radii. So that gives us an enhanced capacity to resist fracture. And from these curves, we use the ASTM procedure to evaluate the JR curves, and we compare the contour integral with the ASTM procedure, and they seem to agree quite well. So this gives us some confidence in the work we're doing. And we've done that for many different notch radii, and we're able to fit kind of a linear relationship between the notch radii and the apparent fracture toughness against the typical crack fracture surface. So we've done this for the four materials. For the notch and for the SCT, the dashed line represents the SCT. So for some materials, for a specific value of tearing, the SCT seems to be conservative, but then the slope changes. So for 0.2 millimeters, which is the typical standard in terms of fracture toughness, it seems to provide a conservative value of J1C for notch radii of above 0.2 millimeters, 0.3 millimeters. And we have fitted a linear relationship for all the different materials. So we've used this in our FAD assessments, and basically you can see that although it was in the safe place, still you have a reduced conservatism in your assessment and an increase in the reserve factor on load. So the ability to apply load is increased when you apply when you use these kind of procedures to assess your fracture toughness. Okay, so to wrap up, we know that the fracture toughness, the apparent fracture toughness, depends on not only on material but also on size and geometry and loading conditions. We have used this procedure to evaluate JR curves for different materials and to evaluate basically the initiation fracture toughness and to be able to characterize the behavior of these non-sharp defects in terms of tearing curves. This is not a finished work. We will try to apply this in our future work to be able to compare the level of conservatism in different components and try to improve our assessments by means of using this SCT specimen value. Basically, we could use a two-parameter fracture mechanics approach to compare the level of constraint, and if we can match that constraint to the SCT specimen, that also tells us that the JR curve for this specimen is useful and is conservative. Thank you.